Welcome everyone. Please recall while studying Fourier series and Dirichlet conditions, we learned that the sufficient condition for having Fourier series of a periodic signal requires the signal to be square integrable over a complete cycle. That means integration of xt square dt over one cycle should be a finite number. Then we approached Fourier transform by considering signals with infinite time period. Therefore, naturally, the sufficient condition for having Fourier transform of a signal demands the signal to be square integrable over minus infinity to plus infinity. That is xt square dt integrated over minus infinity to plus infinity should be a finite number. However, this condition is not a necessary condition. Please recall, we have found that Fourier transform of the signal 1 is equal to 2 pi delta omega, and 1 is a signal which is constantly 1 for all time starting from minus infinity to plus infinity. Therefore, the integration of square of 1 from minus infinity to plus infinity is not a finite number. So 1 is not a square integrable signal. However, using a delta function, we can still express Fourier transform of this signal. Similarly, Fourier transform of ut, we said, is 1 over j omega plus pi delta omega. However, once again, integration of ut square from minus infinity to plus infinity, or 0 to infinity for this case, is again not a finite number. So square integrability is not a necessary condition for existence of Fourier transform. Now consider a signal which is continuously increasing with time like this, such that if you square the signal and calculate the integration of x square up to time equal to infinity, the result is going to be infinite or unbounded. So this signal is not square integrable, and this signal also therefore may not have a Fourier transform. So we cannot express this signal as a sum of exponential signals using the Fourier transform as we did before. However, there is still a way, a method, using that it may be possible to express this signal as a sum of exponential signals, and that method is called Laplace transform, which we are going to study now. Suppose, consider an exponentially decaying signal like this. Call this signal as e to the power minus sigma t, where sigma is a real positive number. So this signal will decay continuously with time. Now let us consider the product of xt and e to the power minus sigma t. Xt increases with time, e to the power minus sigma t decreases with time. And now if the rate of decrease of e to the power minus sigma t is faster than the rate of increase of xt, then it may be possible that this product will eventually decrease with time. If e to the power minus sigma t is decreasing faster than the rate of increase of xt. And then it may be possible that the square of this product is integrable from minus infinity to plus infinity. So this integration may be a finite number. Under that situation, we can calculate Fourier transform of this product. Although we cannot calculate Fourier transform of xt alone, but Fourier transform of this product xt e to the power minus sigma t will exist. And also this Fourier transform of the product of xt and e to the power minus sigma t can be calculated in the usual way as integration of this function, which is the product in this case, multiplied with e to the power minus j omega t dt integrated from minus infinity to plus infinity, which you may write as integration of xt e to the power minus sigma plus j omega with this t common dt from minus to plus infinity. Now notice that this number sigma plus j omega is a complex number. Sigma is a real number, omega is a real number. Sigma plus j omega together is a complex number. And let me give it a new name. So let me define sigma plus j omega is equal to s, a complex number, of course. Then this integration can be written as xt e to the power minus st dt from minus infinity to plus infinity. This is nothing but the Fourier transform of xt multiplied with e to the power minus sigma t. Now, after you perform this integration, the variable t will be gone and the result will be a function of this s, which is equal to sigma plus j omega. So this I will write as a function of s, capital X of s, because it will depend on s. This function is called the Laplace transform of x of t. We will denote this with this curly L, Laplace transform of x of t, which is nothing but Fourier transform of xt multiplied with e to the power minus sigma t. Now, once we have the Fourier transform of this product, then using Fourier inverse, we can write this product as the Fourier inverse of this signal, this function capital X of S, which is by definition 1 over 2 pi integration of this X of S e to the power j omega t d omega, omega running from minus infinity to plus infinity. From this we can also write that xt is equal to 1 over 2 pi integration of x of s e to the power j omega t d omega, omega running from minus to plus infinity, and then I have to multiply this with this e to the power plus sigma t, this thing multiplied with e to the power plus sigma t. Now I can put this e to the power sigma t inside this integration, because the integration is over omega and this term e to the power sigma t does not depend on omega. So this is equal to 1 over 2 pi integration of x of s e to the power j omega t and e to the power sigma t put inside, then multiplied with d omega, omega running from minus infinity to plus infinity. You may club these two exponential terms together in this way as e to the power sigma plus j omega with t common. This is equal to 1 over 2 pi integration over omega equal to minus infinity to plus infinity capital X of S e to the power sigma plus j omega is by our definition same as S. So let me put e to the power st here and d omega. Now since S is equal to sigma plus j omega, I can write d omega is equal to ds divided by j or multiplied with minus j. So let me substitute d omega here with ds and a minus j here, and the integration is over omega, that is the imaginary part of s, okay, imaginary component of s, omega running from minus infinity to plus infinity. This is called Laplace inverse. Now you note carefully what we have done through this mathematical jugglery is nothing but we have expressed xt, this signal, as a sum of many exponential signals. E to the power st, this part is an exponential signal which is multiplied with some coefficient or amplitude which is capital X of S, and then all these exponential signals are added or integrated together to get the signal small xt. So in this way, a signal like this which by itself is not square integrable and does not have a Fourier transform can also be written as a sum of exponential signals in this way using Laplace transform. And the amplitude or amount of each of these exponential signals, that is capital Xs, is given by this. Capital Xs is the Fourier transform of xt e to the power minus sigma t. That is this. This is equal to capital Xs. So with this formula you can determine capital Xs, which is the Laplace transform of small xt, and then the signal small xt can be written as a sum of many exponential signals with coefficients or amplitudes given by this Laplace transform. Now you may be thinking that why is it necessary to write a signal as a sum of exponential signals always? So that question is really very important. However, I will tell the answer after a few days. For now, you should believe in your instructor that this is really very useful to be able to express a signal as a sum of exponential signals. Okay, now coming to another important thing. Here we are multiplying this increasing signal xt with this exponentially decreasing signal e to the power minus sigma t. Now the rate of decrease or decay of this signal depends on the value of sigma. If you take a larger value of sigma, then this signal will decay at a faster rate like this. And if you take a smaller value of sigma, it will decay at a slower rate like this. So these are different possible curves for continuously increasing values of sigma. Now we are multiplying e to the power minus sigma t with xt so that this product becomes square integrable. However, if we pick a small value of sigma, then this product may still be increasing or may still be not square integrable. Only if we take a large enough value of sigma so that this signal is decaying fast enough, then this product will be square integrable. For example, if you take say a small value of sigma, very small, close to 0, then e to the power 0 is like 1, and if you multiply xt with 1, then nothing is going to change. Xt will still be increasing and this will still be not square integrable. So this product will be square integrable only for sigma having a large enough value, say greater than a minimum required value, and then only this Fourier transform of this product will exist. So this Fourier transform exists for sigma being large enough. Now by definition, this Fourier transform of this product is nothing but Laplace transform of xt. I mean, this Fourier transform is called the Laplace transform of xt, which we wrote here. Okay, so this Fourier transform is called the Laplace transform, which we are writing as a function of s, where s is nothing but sigma plus j omega. And this Fourier transform or Laplace transform, which is given by this integration, will exist only if sigma is large enough. Okay, so this Fourier transform exists only for a set of values of sigma and not for all values of sigma. In other words, xs is finite, or it exists for some values of s and not for all values of s, when the real part of s, that is sigma, is large enough, then xs exists, otherwise it does not exist. So we call it, let me write here, we call it a region of convergence, or ROC in short. This means the set of values of s such that this integration is finite, or this integration converges, or that this capital Xs is finite, or it exists, okay, such that X is exists or converges. I mean, basically this integration converges to a finite number. Okay, that is called the region of convergence of Laplace transform. And of course, this will depend on the signal xt itself. If the signal xt is increasing quite fast, very fast, then you have to choose a larger value of sigma to make this product square integrable. However, if this signal xt is increasing very slowly, then even a small value of sigma may be sufficient to make this product square integrable. So the region of convergence of Laplace transform definitely depends on the signal xt we are considering. Now you may be thinking that e to the power minus sigma t is decreasing towards the right, but it is increasing towards the left. So when we multiply xt with e to the power minus sigma t, then the right side portion of xt will be brought down, but the left side portion of xt will be magnified, and therefore this product may not remain square integrable indeed. Indeed, that is possible, yes. However, often we will deal with signals whose value is 0 before some point of time. Such signals are called causal signals, and for such signals there is no problem. Since the signal itself is 0, when you multiply that with e to the power minus sigma t, that will still remain 0. Okay, now this point of time where this signal starts, we can take that as t equal to 0 without loss of generality. So let me define causal signals. Causal signals are signals xt such that xt equal to 0 before some point of time, which we can take as t less than 0 without loss of generality. Now Laplace transform of any signal xt is given by it is here the Laplace transform, which is same as the Fourier transform of xt to the power minus sigma t, which is same as this integration. Okay, so Laplace transform is integration of xt e to the power minus st dt, t running from minus infinity to plus infinity. This is true for any signal xt, but if this signal xt is causal, then we can write this as integration of xt e to the power minus st dt, t running from 0 to infinity. This is if xt is causal. Because if xt is causal, then value of x is 0 before t equal to 0. This is also called one-sided Laplace transform. Now a very important fact I would like to make it clear. This integration from time 0 to infinity means including the time 0. Okay, or for your understanding, you may call this as from 0 minus to infinity. This is because while calculating Laplace transform of any signal, I can always shift my origin t equal to 0 at the starting point of that signal. Now suppose you are considering a delta signal, which we often deal with, and a delta signal starts and ends at t equal to 0, delta t. Okay, now if we want to calculate Laplace transform of this signal, so we have to multiply this with e to the power minus st, something like maybe like this, some e to the power minus st, and then we have to integrate it. We have to make sure that the signal delta t is not missed out while we do the integration. If we start our integration from say 0 plus up to infinity, then the entire signal delta t will be missed. So it is conventional or customary to do this integration from point 0 minus, such that while dealing with delta functions, the functions are not missed out during the integration. Let us now calculate the Laplace transform for some simple common functions and also look at the properties of Laplace transform. To begin with, let us calculate the Laplace transform of delta t, that is an impulse function. Now Laplace transform is given by this formula here. Okay, so accordingly Laplace transform of delta t will be integration of delta t e to the power minus st dt, t running from minus infinity to plus infinity. Now, using the property of delta function, we can write this integration as equal to e to the power minus s 0 in place of t. So that is equal to 1, and that is the Laplace transform of delta t. Now next, let us try to calculate the Laplace transform of ut, that is unit step function. So that will be equal to integration of ut e to the power minus st dt, t running from minus to plus infinity. Now this is equal to integration from t equal to 0 to infinity, because before time 0 u is 0, so we can change the limit of integration as t equal to 0 to infinity, and within this range, that is after time 0, value of u is 1. So let me put 1 here, then e to the power minus st dt. Now this integration will be equal to e to the power minus st divided by minus s with limits infinity and 0. Yes, of course, s should not be equal to 0, okay, otherwise we cannot divide by s. Now this we may also write as e to the power minus sigma plus j omega t divided by minus sigma plus j omega. That is, I am replacing s with sigma plus j omega. Sigma is the real component of the complex number s, and omega is the imaginary component of the complex number s. Okay, now this is equal to e to the power minus sigma infinity multiplied with e to the power minus j omega infinity minus e to the power 0 whole divided by minus sigma plus j omega. Now this term e to the power minus j omega multiplied by something always has a modulus equal to 1. Okay, the modulus of e to the power minus j omega t for any t is equal to 1, and e to the power minus sigma infinity, its value depends on sigma. Sigma is a real number, and if sigma is positive, then e to the power minus sigma infinity is 0, because e to the power minus a large positive number, very large positive number, gives 0. So for that case, we can write this as 0, this term, minus e to the power 0 is always 1 divided by minus sigma plus j omega. Okay, so this is true if sigma is greater than 0. If sigma is less than 0, negative, then e to the power this will be a very large positive number. E to the power a large positive number will be unboundedly large, and therefore the result of this integration will be infinite. Okay, so this result is true only if sigma is greater than 0, and if sigma is greater than 0, then s is also not 0. We can do this integration by dividing with s here, no problem. So I will write this is equal to minus minus plus 1 divided by sigma plus j omega, or I can put back s in place of sigma plus j omega. So this is true if sigma is greater than 0. Otherwise this integration is not converging. Okay, so Laplace transform of ut is equal to 1 over s, but this is true if sigma greater than 0, that means or the real part of s is greater than 0. In fact, this is the region of convergence. Only if the real part of s is greater than 0, for those values of s, Laplace transform of ut exists. Otherwise, Laplace transform of ut does not exist. Now, you recall that the result of Fourier transform we represented using a graph that we called spectrum. Similarly, the result of Fourier transform can also be viewed graphically, but now the Laplace transform is a function of s. S is a complex number which has two components, real and imaginary. However, previously when we did Fourier transform was a function of one variable only, omega, but Laplace transform is a function of two variables, sigma and omega, okay, which are the real and imaginary components of s. Therefore, now to plot the Laplace transform of a function, we have two independent variables. So therefore, we will need a two-dimensional plane, basically a complex Argand plane, where these two axes will denote sigma and omega respectively. That means the real component of s and the imaginary component of s. Remember that s is equal to sigma plus j omega. Okay, now consider the Laplace transform of ut. This is valid only if sigma is greater than 0. That means on this side, that is the left side, in the left side Laplace transform does not exist. So here Laplace transform of ut does not exist, and on this side Laplace transform of ut exists, and it is equal to 1 over s. Now suppose you consider a point here which is, say, sigma equal to 2, and say here omega is equal to 1. So this point is the point where s is equal to 2 plus j into 1. So at this point, the value of Laplace transform of ut will be equal to 1 over 2 plus j at this point. Okay, so this is the value of Laplace transform of ut at this point. Similarly, if you consider any other point, like here, say this is -1, this is 1, so consider this point. At this point, the value of Laplace transform of ut is equal to 1 over s, and s at this point is sigma plus j omega, 1 plus j1. In this way, each and every point on this side, the right side, will have some value of the Laplace transform for ut. Okay, and this side is the region of convergence for the Laplace transform of ut. So this side is the region of convergence. This quadrant is also within the region of convergence of this Laplace transform. Now, just a quick note, here this is the formula for Laplace inverse of any signal. So what we have to do, we have to take the Laplace transform and then multiply it with e to the power st, and then integrate it from omega equal to -infinity to +infinity. And with the sigma, of course, belonging to the ROC. What I mean that the value of sigma should be such that this integration is carried within the region of convergence of this Laplace transform. Okay, so if you want to calculate the Laplace inverse of 1 over s, okay, so the Laplace transform here is 1 over s. If you want to calculate the Laplace inverse, all you have to do, you have to pick some value of sigma greater than 0, okay, and say I choose a large enough sigma value, say something here quite large, and then I will choose different omega values for this sigma. For this sigma, I will choose different omega values starting from -infinity to +infinity, and then on this line, on a line like this, I will consider 1 over s, and then I will multiply it with e to the power st, and then I will do this integration over ds starting from omega equal to -infinity to infinity over this line, okay, and then this I have to multiply this with -j by 2 pi, okay, that is the formula of Laplace inverse, so -j by 2 pi. Then this is the Laplace inverse of 1 by s, so that should give me back the Laplace inverse of 1 by s, which is ut, because Laplace transform of ut is 1 by s. Okay, nice. However, in practice, we will actually not calculate Laplace inverse in this way. We will do that much simply later. Okay. Next, let us calculate, say, the Laplace transform of u minus t. Okay, how does this signal looks like? This is 1 before time 0 and then it is 0. This is u minus t. Now this will be equal to integration of u minus t e to the power minus st dt, t running from minus to plus infinity. However, it is enough to do the integration from minus infinity to 0, and within this region u minus t is equal to 1 multiplied with e to the power minus st dt, and then this will be equal to e to the power minus st divided by minus s with limits t equal to 0 and minus infinity, provided s is not 0, and then this is same as e to the power 0 minus e to the power minus infinity into t. So this will be minus minus plus st divided s infinity divided by minus s, which is same as 1 minus e to the power sigma infinity multiplied with e to the power j omega infinity divided by sigma plus j omega, replacing s with sigma plus j omega. Now here e to the power j omega infinity is a finite bounded number with modulus equal to 1. E to the power sigma into infinity, sigma is a real number, so if sigma is positive, this will be a very large number, so this integration will be infinite. But if sigma is negative, then this will be a very small number, 0, and then we can write this as 1 minus 0 divided by minus sigma plus j omega. This is of course if sigma is negative, and then this is equal to minus 1 by s. S is sigma plus j omega. Okay, so this Laplace transform or this integration is convergent only if sigma is less than 0, and that is the region of convergence for this signal. Okay, now next, suppose the Laplace transform of some signal xt is equal to call it xs. Okay, then the Laplace transform of k times xt will be equal to k times Laplace transform of xt, that is capital Xs. This I shall leave as a homework for you. Next, now considering this property, Laplace transform of minus u minus t, that will be equal to minus of Laplace transform of u minus t and this is equal to minus of this is minus 1 by s. So minus minus plus 1 by s. This is quite interesting to note that the Laplace transform of this function is same as the Laplace transform of ut. For ut, Laplace transform is 1 by s, and for minus u minus t, this is again 1 by s. However, the two signals are quite different. Okay, ut is like this. This is 0, this is 0 here, 1 here, this is ut, and minus u minus t, that will be like this. So minus 1 before time 0 and then 0. Two signals completely different has same Laplace transform. However, there is a difference. The difference is that for minus u minus t, the ROC, region of convergence, should be same as the region of convergence of u minus t, which is sigma less than 0. So this has the region of convergence sigma less than 0. However, Laplace transform of ut is also 1 over s, but region of convergence is sigma greater than 0. Okay, that is the difference. So if you want to plot the Laplace transform of u minus t, that will look like this. Here I plot sigma, here I plot omega or j omega, because this is the imaginary part. Okay, so for u minus t, this side here Laplace transform is not defined, but here the Laplace transform is defined. Okay, this is quite opposite to the case of ut. However, in this course we will not deal with this type of signals minus u minus t, which is not causal. Okay, so recall that a causal signal is a signal whose value is 0 before some time. Okay, but u minus t is constantly 1 up to minus infinity, so that is not causal, and we cannot make it causal by changing the origin. We will not talk about those kind of signals in this course most likely, and we will talk about causal signals only, and for which the region of convergence will be always like sigma greater than some minimum sigma value. Okay, so for causal signals that we will talk about, the region of convergence will always be towards the right. Okay, it may start from the origin, or it may start after some minimum sigma value, but it will be towards the right. It will never be towards the left like u minus t. We will not consider those non-causal signals here. Okay, next property, suppose the Laplace transform of x1 plus x2 is required, this will be equal to Laplace transform of x1 plus the Laplace transform of x2. This is again a very easy one to prove, so this is your homework. Next, number 7, if the Laplace transform of a signal xt is known, that is say capital Xs, then what will be the Laplace transform of say x t minus t naught time shifted signal? Okay, this is very easy to find out, and we did something very similar for Fourier transform as well. So try it yourself first. Okay, so the Laplace transform of x t minus t naught is equal to integration of x t minus t naught e to the power minus s t dt, t running from minus to plus infinity, and then I will put t minus t naught equal to tau such that dt is equal to d tau, and when t is minus infinity, tau is also minus infinity. If t is plus infinity, tau is plus infinity. So this integration becomes tau equal to minus infinity to plus infinity x tau e to the power minus s. In place of t, I will write tau plus t naught, so tau, and I will write this way minus s t naught. Then in place of dt, d tau. Now this is a constant that you can write outside the integration symbol. So this is e to the power minus s t naught, and we have x tau e to the power minus s tau d tau, tau running from minus to plus infinity, and this integration is nothing but the Laplace transform of small x. So this is equal to e to the power minus s t naught capital X s, and that is the answer. So this is e to the power minus s t naught capital X s. Now next, suppose the Laplace transform of xt is again capital Xs, then what will be the Laplace transform of say xt multiplied with e to the power at? Try it yourself first before watching my derivation. Okay, so Laplace transform of e to the power at xt is equal to integration of e to the power at xt, then e to the power minus st dt, t running from minus to plus infinity. Okay, this is by the definition of Laplace transform. Then this is equal to integration of xt, and let me join these two exponentials as e to the power minus s minus a t dt, t running from minus to plus infinity. Now can you recognize what is this right hand side? Okay, so we know since x is, that is the Laplace transform of xt, is equal to integration of xt e to the power minus st dt, t running from minus to plus infinity. That means capital X s minus a will be equal to integration of xt e to the power minus, in place of s I will put s minus a dt from minus to plus infinity, and this is exactly what we have here. So this is equal to capital X s minus a, and that is the answer. So the answer here is capital X s minus a. Okay, so that means if the Laplace transform of some signal xt is capital Xs, then when you multiply the signal with e to the power at, to get the Laplace transform, all you have to do is replace s here with s minus a. Replace s in the original Laplace transform with s minus a. Okay, so as an example of this property, suppose we want the Laplace transform of e to the power at ut. Okay, so how can we get that? Laplace transform of ut is 1 by s. This is for ut alone, and when you multiply that with e to the power at, you have to replace s with s minus a, and that is the answer. Let us see how does this signal e to the power at ut looks like. E to the power at is a exponential signal, so it depends on the value of a. Suppose a is a real number and positive, then e to the power at will be a exponentially increasing signal like this. When you multiply that with ut, since ut is 0 before time 0, the product will become 0, and after time 0 ut is 1, so e to the power at here will remain as it is. So this is the case for a being real and positive. Now what happens if a is real but negative? In that case, we will get an exponentially decaying signal like this. Okay, next, what happens if a is an imaginary number, something like j omega naught, for some value of omega naught? Then the signal e to the power at, which is same as e to the power j omega naught t, we cannot draw that in this two-dimensional diagram, but you may extend your imagination by thinking an argand plane, complex plane, with this axis perpendicular to the board, representing the real part of the signal, and this vertical axis is the imaginary part of the signal. This horizontal line is the time axis. Then e to the power j omega naught t will be a spiral like this, rotating anti-clockwise or clockwise depending on omega naught or is positive or negative. But its magnitude, okay, that will be constant. That will be constant and equal to 1 always. Okay, the magnitude, although my drawing is not good, is constant and 1. Now consider what happens if A is neither purely real, neither purely imaginary, but it's a complex number, something like sigma naught plus j omega naught for some specific value of sigma naught and omega naught. Then the signal e to the power at is equal to e to the power, let me write here, e to the power at is equal to e to the power sigma naught plus j omega naught t, which is equal to e to the power sigma naught t plus multiplied with e to the power j omega naught t. Now, and we also have ut, of course, multiplied with this. Now let me draw this part first, e to the power sigma naught t. That will be a signal like this, assuming sigma naught greater than 0. And then e to the power j omega naught t, that will be a spiral in the three-dimensional argand plane we are considering. So that will be a spiral like this. I'm drawing with dotted lines. Now this spiral has a constant magnitude. When you multiply these two signals, then what will happen is this. We will get a spiral whose magnitude will increase constantly with time, and this e to the power sigma naught t will act as the envelope or boundary of this increasing spiral. Okay, in the same way, if you consider A equal to sigma naught plus j omega naught, with sigma naught being a negative number, then we will get a spiral, imaginary spiral, whose amplitude will continuously decay in this way. Okay, now next thing, we already know that the Laplace transform of this signal is 1 by s minus a. However, I would like to look at the ROC of Laplace transform of e to the power at ut. For that, let me write this Laplace transform as equal to integration of e to the power at ut, then this signal multiplied with e to the power minus st dt, t running from minus to plus infinity. Now this will be same as the integration from time 0 to infinity, and in this range u is 1, and these two exponentials can be written together as e to the power minus s minus a t common dt. Okay, now let me put in place of s sigma plus j omega, and in place of a sigma naught plus j omega naught t dt from time 0 to infinity. Okay, so I repeat, s is equal to sigma plus j omega, and a is sigma naught plus j omega naught. A is a given arbitrary number, arbitrary complex number, whose real and imaginary components are sigma naught and omega naught, and these are given. Okay, because these are the properties, parameters of the given signal e to the power at. And S is the variable, sigma and omega being its real and imaginary components, and this integration will be a function of sigma and omega. That means this integration will be a function of S. Yeah, we already know that Laplace transform gives us a function of S. Okay, so now this is equal to integration of e to the power minus sigma minus sigma naught t multiplied with e to the power minus j omega minus omega naught t dt, t running from 0 to infinity. Now the question is, when will this integration converge and be finite? Notice that this term, this is e to the power pure imaginary number. So the modulus of this signal, amplitude or magnitude of this part is always equal to 1. But the amplitude of this signal will change with time. Sigma and sigma naught, these are real numbers. So if sigma minus sigma naught is positive, then this will decay continuously, and then this overall signal will also decay and the integration will converge. So this will be finite if sigma minus sigma naught is positive, that is, or sigma is greater than sigma naught. Otherwise this number will be negative, and so overall we have e to the power something positive multiplied with time, so that will increase continuously and integration will be unbounded, non-converging. Okay, so this Laplace transform or this integration is possible only if sigma is greater than sigma naught, where sigma naught is given as the parameter of the given signal e to the power at. So ROC of this signal is specified by sigma greater than sigma naught. So if I draw a diagram again with sigma and omega, then this Laplace transform is valid only if the value of sigma is greater than sigma naught. Okay, so this side is the ROC, and here or here or here or here Laplace transform is undefined. Okay, so as I told you previously, for causal signals, ROC is always on the right side of this diagram. We call it the S plane, because S is sigma plus j omega. So ROC is always somewhere in the right side of the S plane for causal signals. Okay, that's for today. See you tomorrow.